Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss dielectrics, classification of dielectrics and polarization of dielectric. Let's begin. Dielectrics are the materials. The classification of materials treated as conductor, semiconductor, insulators, but it is in the category of insulators, in which all the electrons are tightly bound to the nuclei of atoms and there are no free electrons to carry current. In case of conductor, there are number of free electrons, that is why electric current flow through that of conductor, but in case of insulator there are no free electrons and these electrons are tightly bound to the nucleus of that of particular atom. Hence, we can say the electrical conductivity of dielectric is very low, means it is not suitable to flow electric current throughout it, and the electrical conductivity of an ideal dielectric is 0. When that dielectric is placed in an external electric field and induced charges are produced on its surfaces. Some examples of dielectrics: glass, mica, wax, air, water, etc. are some examples of dielectrics. Now, classification of dielectrics. If we consider a molecule, there are equal number of positive and negative charges are present. Here the negative charge in the form of electron clouds and the positive charge, equal amount of positive charge throughout that of nuclei. Inside the atom there are proton and neutron, outside that of nucleus electrons revolving around that of nucleus. So, in that case of molecule, equal amount of positive and negative charges are there. So, the electrons are revolving around that of nucleus and positive charge within that of nuclei. In such a molecule of a dielectric, the centers of gravity of positive and negative charge, here the negative charge, here the positive charge, may or may not coincide. These two charges may or may not coincide. Likewise, if these molecules are coincide or not, accordingly they are classified as polar molecules and non-polar molecules. So, what is polar molecules? The molecules in which the centers of gravity of positive and negative charges do not exactly coincide are called polar molecules. Here the centers of positive and negative charges do not coincide. So, these are named as polar molecules. And in case of non-polar molecules, the molecules in which center of gravity of positive and negative charges coincides, and these are named as non-polar molecules. In case of polar molecules, they have symmetrical shapes and have permanent electric dipole moments. They have symmetrical shape and possessed permanent electric dipole moment. Some examples: hydrochloric acid HCl, ammonia NH3, carbon dioxide CO2, water H2O, etc. are the examples of polar molecules. In case of non-polar molecules, they have symmetrical shapes sorry, here in case of polar molecules they are unsymmetrical shapes, but in case of polar molecules they are symmetrical shapes and have no electric dipole moment. Some examples: H2, Cl2, O2, N2 etc. are under non-polar molecules. Now, what exactly happens when these dielectrics are placed in case of external electric field? What happens to that of polar molecules and that of non-polar molecules? First we take, in the absence of external electric field, these polar molecules form a closed chains. In the absence of electric field, negative, positive, 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 negative, positive. This is in the absence of electric field. In the absence of electric field, these polar molecules form closed chains. Hence, the net electric dipole moment of these molecules is 0. Here the net electric dipole moment will be 0. When an external electric field is applied, but when an external electric field applied, these polar molecules experience torque and these closed chains are broken and the molecules try to align themselves in the direction of electric field. Here we take, in the presence of electric field, what happened? In the presence of electric field, when an external electric field is applied, so the polar molecules experience a torque and they try to align themselves in the direction of electric field, like this: negative, positive, 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 negative, positive. They are aligned themselves in the direction of electric field. But this tendency of molecules to align in the direction of electric field is opposed by the property of thermal agitation. As in case of thermal agitation increases with increase of temperature, hence above 0 degree Kelvin temperature only partial alignment takes place. Therefore, the degree of alignment increases with increase of strength of electric field and decrease of temperature. With the increase of electric field and with the decrease of temperature, the strength of alignment increases. Okay? This is for polar molecules. This one in the absence of electric field, that one in the presence of electric field. This is the presence of electric field, that one the absence of electric field. Again, similar situation in case of non-polar molecules. As we take non-polar molecules, in the absence of electric field, in the absence of electric field, each molecule has no permanent electric dipole moment. As we say, all the positive charges in the molecule experience force in the direction of the field, and all the negative charge means the electrons experience force in the direction opposite to that of electric field. Okay. That situation arises when we apply electric field to that of non-polar molecules. But in case of absence of electric field, the positive and negative are coincide. Since it has no electric dipole moment, as we applied external electric field in the presence of electric field, what happened? Look at that particular picture. When an electric field is applied here, so that molecule looks like this, negative and positive. How exactly that happened here? In the presence of applied electric field, all the positive charges in the molecules experience, all the positive charges in that of molecule experience in the direction of electric field, and all the negative charges means the electrons experience force in the direction opposite to that of electric field. Hence, center of gravity of positive and negative charges are displaced in opposite directions. Thus, each non-polar molecule in the electric field becomes an induced electric dipole. Here the electric dipole due to the induced electric dipole, and it has induced electric dipole moment, and the net effect of external electric field is same on a dielectric whether it is polar or whether it is non-polar. That does not depend upon the polarity of that of dielectrics. The net electric dipole moment does not depend upon the polarity of that of dielectric, and the molecules get aligned in the direction of electric field, or dielectrics gets polarized. This is in case of non-polar molecules. This is the polar molecules, this is non-polar molecules. These are the points, the differentiation of polar molecules and non-polar molecules. What exactly happened in the presence of electric field and in the absence of electric field. Now, how the process of polarization takes place in case of dielectrics. Discuss polarization of dielectric. Look at a point here to remember that point. When a dielectric placed in an external electric field, induced charges are produced on its outer surface. That point can be explained throughout that process, polarization of dielectric. Okay, let us see. Here we discuss if the molecule of a dielectric are polar, then the absence of external electric field, the molecules are randomly oriented and the net dipole moment of the dielectric is 0. Here we studied. In case of dielectric with non-polar molecules, the net dipole moment of the dielectric also 0 in the absence of electric field. So, Let me consider a dielectric slab, whether that is polar or non-polar. A dielectric slab that is either polar or non-polar, that does not mean. Slab A, B, that placed in an external electric field between the plates of a charged parallel plate capacitor. So, here we take a charged parallel plate capacitor, two plates of that of charged parallel plate capacitor, the charge plus q here, these plates positive charge, then minus q negative charge, placed in an external electric field. The strength of that of external electric field inert. Okay. Let the strength of external electric field between the plates is inert. The presence of external electric field will shift the center of gravity of positive and negative charges of the molecules. There are equal amount of positive and negative charges, but due to the presence of electric field, the center of gravity of positive and negative charges are shifted. Positive charges with the direction of electric field and negative charges to the opposite of that of electric field. In case of non-polar molecules, that happened. If the dielectric consists of polar molecules, then in addition of shifting the center of gravity of positive and negative charges, it will also break the closed chain of that dipole. The closed chain of dipole is breaked, and the center of gravity of negative charge will shift towards positive charge. Center of gravity of negative charge moves towards positive charge, and center of gravity of positive charge moves towards negative charge to the plate of that of capacitor. So, look here, the dipoles are organized like this. Negative positive, negative positive, negative positive. These are the dipoles in case of polar molecules that break down to the non-polar, and situations are same for that of polar and non-polar. The dielectric may be polar or non-polar. This one be the dielectric, this one the dielectric. These are the plates, that is the strength of external electric field, external electric field inert. These are the parallel plates. look here, the negative charge towards positive end and positive towards negative end, and this will result in the alignment of dipoles along the direction of electric field, and the positive charge of the molecule inside the dielectric is followed by the negative charge of next molecule and so on, positive charge followed by negative charge and so on. Since the molecules are very close to each other, hence the positive charge of one molecule is cancelled by the negative charge of next adjacent molecule and so on. Hence the net charge, look here that figure, the net charge within the dielectric is 0 except near the surface of that of dielectric. In case of surface of that of dielectric, one end negative charge developed, another end positive charge developed, but within that net charge within dielectric is 0. Now we draw the figure how exactly happened when an external electric field is applied to that of dielectric. So that figure changed to a new one. This is the plate, that end plus Q positive, that end negative charge. There will be the dielectric. Inside that of dielectric, at A end negative charge, at B end positive charge, with the application of external electric field E naught. The net negative charge will appear on that of surface A and net positive charge on surface B of that of dielectric. The appearance of net negative charge and positive charge on opposite faces of the dielectric produces an electric field. Here an electric field is produced, and that electric field, this produced electric field, that is EP. Okay. Within that of dielectric, the produced electric field is EP, and this field acts in a direction opposite to the applied electric field. Here the direction of applied field E naught, that is the direction of developed electric field within that of dielectric from this direction. So these are opposite to each other. Therefore the electric field inside the dielectric is reduced. Here the developed electric field inside that of dielectric will be reduced. So the net electric field inside the dielectric, therefore the net electric field inside the dielectric will be E, net electric field is equal to E naught minus EP. E naught the external electric field, EP the electric field developed within that of dielectric. Therefore, when a dielectric slab is placed in an electric field, then the strength of electric field will decrease. Here the strength of that of electric field will be decreased, and the phenomenon of appearance of charges on opposite face of that of dielectric slab induced by that of external electric field, and that process is named as polarization. So, here we write, hence when a dielectric slab is placed in an electric field, the strength of electric field will decrease. As we mathematically write here, the strength of electric field will decrease, and the phenomenon of appearance of charges on opposite faces of a dielectric slab induced by external electric field is called polarization. Okay. The appearance of negative charge and positive charge at the two end of that of surface of dielectric, that process is known as polarization, and due to that of polarization, the strength of electric field decreases. Now, the charges on the surface of plates, here in case of parallel plate capacitor, the charges on the surface of the plates of the parallel plate capacitor is known as free charge. We define what is free charge. Free charge the charges on the surface of the capacitor, surface of plates of a parallel plate capacitor is called free charge. The charges on the surface of the plates of a parallel plate capacitor is known as free charge, and the surface density due to this free charge is called surface density of free charge. Surface density due to this free charge is called surface density of free charge. Surface density of free charge, that denoted by sigma f. Surface density of free charge, this is due to free charge, the concept of free charge. Next, bound charge or induced charge. The induced charge, the charge are induced, the induced charge on the surface of a polarized dielectric, this is the polarized dielectric, is called bound charge. Next, the concept of bound charge. Okay. Bound charge. The induced charge, the induced charge on the surface of a polarized dielectrics, polarized dielectric is called bound charge, and the surface density due to the bound charge surface density, charge per surface area. The surface density due to that bound charge is called surface density of bound charge. Surface density of bound charge, and it is denoted by sigma p. Surface density of bound charge, and the surface density due to that of bound charge is known as surface density of bound charge, sigma p. This is the surface density of free charge, sigma f. Due to that polarization process, the charge is developed, that is why sigma p, this is for free charge. So, with the help of this video lecture, we understand the concept of dielectrics, examples of dielectrics, classification of dielectrics as polar molecules and non-polar molecules, and some basic points towards polar molecules and non-polar molecules, and what happenings to that of polar molecules and non-polar molecules in the absence of electric field and in the presence of electric field. And finally, the process of polarization of dielectric, how polarization takes place when an external electric field is applied to that of dielectric, whether the dielectric may be polar or non-polar. Due to that of process of polarization, the net electric field inside the dielectric will be decreased, and the phenomenon of appearance of that of charges on that of opposite set faces of dielectric is known as polarization. And what is free charge and surface density of free charge, bound charge, surface density of bound charge. So, with this useful and informative notes, let me wind up this session. Thank you.